Welcome to the deep dive. Today we're jumping into something pretty core for developers, picking the right place to store your data.
Yeah, it's a big one.
We're going to zoom in on AWS DynamoDB. You know, it's that cloud native database they push, promises amazing speed even when things get huge.
Right, stable performance at scale, that's the promise.
But is it always the right answer? That's what we want to figure out today. Our goal really is to get under the hood of DynamoDB, see where it shines, but also, what the trade-offs are.
Exactly. So you can decide if it fits your project without getting totally overwhelmed by the tech jargon.
And we're leaning on some insights from DynamoDB Decoded, when it shines, and when to look elsewhere to guide us.
Good source. So maybe let's start at the beginning. Like, why does DynamoDB even exist? What problems was it trying to solve?
Good question. Where do we start? Traditional databases.
Yeah, the source kicks off right there, looking at the struggles you hit when trying to scale old school relational databases.
Okay, let's unpack that a bit. What kind of hurdles are we talking about typically?
Well, the big one is that they often live on just one server. Think of it like, I don't know, a single cashier at a busy store.
Right. Eventually the line gets way too long.
Exactly.
Mm-hmm.
The source even shows this visually. More requests hit that one server, and performance just tanks.
So these databases, they're powerful, but they kind of have a built-in speed limit on their own.
Okay, so people must have ways to deal with this, right?
Oh.
What are the usual fixes for relational databases?
Oh yeah, there are standard plays. One is setting up a main database and then adding read-only copies, read replicas, they call them.
Helps spread out the reading work, I guess.
Precisely. Take some load off. Another way, more involved, is sharding. That's where you basically chop your big database into smaller, separate ones.
Sounds complicated. Do these fixes have their own, let's say, headaches?
They definitely do. With read replicas, okay, reads are faster maybe, but the main database still has to handle all the writes. If you've got loads of data coming in, it can still choke.
Okay. Still a bottleneck potential. Yeah. And just keeping those copies synced up adds complexity too. Sharding, that's a whole other level.
How so?
Your application suddenly needs to be smart enough to figure out which little database piece has the data it needs. You have to build in routing logic.
Ugh, okay.
And then, data isn't always accessed evenly. So you might end up with one shard getting hammered while others are just sitting there. An unbalanced system. You have to constantly rebalance things.
Sounds like a real pain to manage. So DynamoDB comes along and says, what? How does it approach this scaling thing differently?
This is really its core selling point. It takes on that job of splitting your data and spreading it across lots of storage units, partitions, and it does it automatically.
Automatically. So no manual splitting or managing those pieces?
Nope. DynamoDB handles routing the requests to the right partition and rebalancing the data if one part gets too busy. It's all happening behind the scenes. The idea is you just throw data at it, and it figures out how to handle the load.
Okay, that sounds appealing. Less operational burden. What about keeping data safe? The source mentioned durability.
Yeah, that's foundational. Your data in DynamoDB isn't just in one place. It's copied to 3 separate physical locations in different availability zones within an AWS region.
So like having backups in different buildings nearby.
Kind of, yeah. It really cuts down the risk of losing data if some hardware fails or there's a bigger issue in one zone. You don't have to set up complex replication yourself.
Another interesting point was this consistency-aware thing, how DynamoDB deals with making sure data is up to date when you read it. What's that about?
Right, so it gives you a choice. You can ask for strong consistency, which means when you read data, you're guaranteed to get the absolute latest written version, always.
Okay, makes sense.
Or you can choose eventual consistency. This is usually faster and cheaper performance-wise, but there's a small chance, like right after an update, that you might read the slightly older version for a very brief moment.
So you trade absolute up to the millisecond accuracy for potentially better speed or cost?
Exactly. And having that explicit choice is really useful. For something critical like, say, inventory counts, you probably want strong consistency. For maybe user session data, eventual might be fine and faster.
And performance itself seems key. Consistently fast, the source says.
Yeah, that's a major draw. It mentions typical reads and writes for single items are usually under 20 milliseconds. That's pretty snappy and crucially consistent, even as you scale up.
20 milliseconds is fast. And they gave that wild example, Amazon itself hitting 146 million requests per second on DynamoDB during Prime Day 2024.
Yeah, that really drives home the scale it can handle. But, no silver bullets.
Right. Every tech has its quirks. So let's get into the fine print the source talks about, the limitations.
Okay, first up, item size. There's a hard limit. You can't store more than 400 kilobytes in a single item, and that includes your data and the names of the attributes themselves.
400 KB, how does that compare? Is that a lot or a little?
Well, compared to something like MongoDB, which might allow 16 megabytes, it's quite small. But the real kicker is how it interacts with the next limitation.
Which is?
No joins. You can't do SQL-style joins to pull related data together from different tables at query time.
Ah, okay. So if you can't join related data easily, you might try to stuff more into that single 400 KB item.
Exactly. That's the implication.
What?
Because you can't join, the common pattern is denormalization, putting related data together in one item. And that can make you hit that 400 KB limit faster than you might think if you come from a relational world.
So you have to really plan your data structure differently. The source mentions compression as a workaround.
Yeah, you can compress data within the item, but the 400 KB limit on the total item size still applies.
Yeah.
It might help you squeeze more in, but it doesn't remove the fundamental constraint. It forces a different way of thinking.
Okay, so no joins forces denormalization, which runs into the size limit. What else? Querying seems different too.
Definitely. The source calls it reduced query capabilities. You primarily query using the primary key.
Okay.
Now, this key has two parts, a mandatory partition key and an optional sort key.
Partition key and cert key, how do those work?
The partition key is fundamental. It basically decides which physical partition, which storage chunk your data lives on. DynamoDB hashes this key to spread data out.
So it's key for distributing the load.
Absolutely. It's how DynamoDB scales, reads, and writes. It means your most efficient queries are the ones where you know the exact partition key, like looking up a user by their user ID.
And the sort key, what does that do?
Within a single partition, so for all items that share the same partition key, the sort key lets you, well, sort them. And you can efficiently query ranges, like get all orders for customer X placed between date A and date B.
Ah, okay. So partition key gets you to the right shelf. Sort key lets you grab a specific range of books on that shelf.
Nice analogy.
Yep.
Yeah, that's pretty much it. This partition key sort key combo is great for modeling one-to-many relationships efficiently.
But what if you need to search by something else? Not the partition or sort key? Like finding all users in a specific city if city isn't part of the key.
Good point. That's where things get more complex. You need to use techniques like global secondary indexes, GSIs.
GSI?
Think of them as additional separate indexes on your table. You define a different partition key and maybe a sort key for the GSI, allowing you to query efficiently based on those alternative attributes.
So you're essentially creating another view of your data optimized for a different query pattern.
Exactly. And this often goes hand in hand with something called single table design.
Sounds scary.
It can be. It's an advanced pattern where you intentionally put different kinds of data, like users, orders, products, into the same physical DynamoDB table, and then use clever key design and multiple GSIs to support all the different ways you need to access that data.
Okay, so GSIs and single table design are ways to work around the query limits, but they add design complexity.
Definitely. It requires careful planning upfront, but exactly how you'll access your data.
Right. Let's shift to capacity. Reads and writes. The source mentioned WCUs and RCUs.
Yeah, write capacity units and read capacity units. Think of them like tokens you spend. Writing roughly 1 KB of data costs 1 WCU. Reading 4 KB with strong consistency costs 1 RCU.
And eventually consistent reads.
Those are cheaper. You get 2 4 KB reads per RCU.
Okay, so you provision or pay for these units, but there are limits.
Yes, and this is crucial. Each partition in your table has its own limits, currently 1,000 WCUs per second and 3,000 RCUs per second.
Per partition, not for the whole table.
Per partition. So if you have one hot partition key that gets way more traffic than others, it can hit its limit even if the table overall has plenty of capacity.
And what happens if you exceed the limit on a partition?
You get throttled. DynamoDB rejects the request temporarily. Your application needs to be built to handle that, maybe with retries and backoff.
Yikes. But doesn't AWS help with hot partitions?
It does try. AWS monitors partitions and can automatically split ones that are getting too hot, dividing the data and the throughput capacity. It can even isolate a single super hot item onto its own partition.
Ah, okay, so it tries to adapt.
Yes, but that rebalancing isn't instant. It takes time. So designing your keys well to distribute the load from the start is still really, really important to avoid throttling.
Makes sense. So given all these constraints and features, where does DynamoDB actually make the most sense? Where does it really shine according to the source?
Microservices pop up as a strong use case.
Why them specifically?
Because microservices usually have a narrow focus, right? A specific job. That often means their data access patterns are simpler and more predictable. It's easier to design a DynamoDB table that fits those known patterns well within the constraints.
Okay, predictability helps manage the limitation.
Yeah. And sometimes, for background tasks within a microservice, maybe slightly higher latency is okay, so doing a couple of sequential queries instead of a join might be acceptable.
What else? Serverless.
Absolutely. Asynchronous serverless workloads, like stuff triggered by events or messages off a queue, these often have really spiky, unpredictable traffic.
Right. Quiet 1 minute, slam the next.
Exactly. Traditional databases can struggle with managing connections efficiently in that scenario, connection pools filling up, etc. DynamoDB just scales its throughput on demand. You don't worry about connections in the same way. It fits that serverless, event-driven model nicely.
And the cost aspect for spiky traffic.
Yeah, that's another big plus mentioned. Sporadic traffic. With DynamoDB's on-demand pricing, if your app isn't doing anything, you're paying very little, potentially close to zero. Unlike a relational database server instance that's sitting there costing you money $247, even if it's idle.
Ah, cost-effective for variable loads. And avoids noisy neighbor issues you might get on shared databases.
Right. Because of the partitioning and isolation, one busy application is less likely to impact another's performance negatively.
Okay, so microservices, serverless, sporadic traffic, but there must be times when it's not a good fit, right? The Houston we have a problem scenarios.
Definitely. The biggest red flag the source mentions is if you have unknown or constantly changing access patterns.
If you don't know how you'll need to query the data later.
Yeah. If you can't predict your main queries up front, you're flying blind. You risk designing a table structure that forces you into really inefficient, expensive table scans later on. Or worse, needing a complete data migration and restructuring project down the road.
Ouch. Expensive and painful.
Very. And related to that is the complexity of evolving a single table design.
You mentioned that earlier. How does it become a problem?
Well, say you start with a single table design for your current needs. Later, the business needs a new feature that requires querying the data in a totally new way.
Okay.
So you probably need to add a new global secondary index, GSI, to support that query efficiently. But, and here's the catch, that new GSI might need attributes in its key that your existing data items don't even have yet.
So you have to go back and update potentially millions or billions of old records just to add the data needed for the new index.
Precisely. The source uses a content tracking example, initially tracking by content ID, later needing to sort by release year. That required adding the release year to all existing content items before the new GSI could work properly. That backfilling can be a major operational headache.
Yeah, that sounds like a hidden cost of maintenance if requirements change a lot.
It really can be. So the core message seems to be, seriously weigh DynamoDB's scaling and performance benefits against the effort of designing for and living with its constraints, especially if your access patterns aren't crystal clear or stable.
Don't just jump in because it scales.
Exactly. Dig deeper first. Is the scalability it offers something you actually need right now or foresee needing soon? Is the effort of denormalization, careful key design, and potential future backfilling worth it compared to maybe a more flexible relational option?
This has been super helpful, really clarifying the trade-offs. So if we were to boil it down, what's the main takeaway for someone choosing a database?
I think the big thing is, don't write off relational databases. They're still incredibly useful, powerful, and they're evolving too. It's not always about jumping to the newest NoSQL thing.
Look beyond the hype.
Yeah. Really understand your specific needs, your data shape, how you need to query it, your scale, your budget, your team's familiarity. Then see which tool, relational or NoSQL like DynamoDB, is the best fit.
And for DynamoDB specifically, the summary is.
It can be amazing. Super scalable, low latency, cost-effective, especially for certain patterns like we discussed. Minimal operational fiddling with scaling infrastructure. But you have to be aware of and design around the item size limit, the lack of joins, the query constraints, and the capacity per partition model.
Know what you're getting into.
Absolutely. Understand the trade-offs before you commit heavily.
And maybe don't feel locked into just one type of database.
Exactly. Be flexible. Sometimes the best approach is polyglot persistence, using different databases for different parts of your system. Maybe DynamoDB for the high-scale event ingestion, but a relational database for complex reporting, for instance.
Experiment and choose the right tool for the job.
That's the key.
Fantastic. Well, that gives us all a lot to think about. Considering these trade-offs, what are the main access patterns and scale needs for your next project? How does this discussion maybe change how you'd approach picking that persistence layer. Definitely some food for thought there.
It always is.
And hey, if you want more insights like this on database architecture and design, you should subscribe for free to the Architecture Corner newsletter. Just check the details in the description. Thanks for tuning in.